Yes, any questions before we continue? We will be continuing with friction, some of the mechanisms that are causing this friction.
Why is kinetic friction less than static friction?
Okay, that is one question. Now, if you look at this diagram, what was the example that we were discussing? We are exerting a force. Now, if this kinetic friction had, let's say, this value, let's say such a graph, I increase the force that I exert, no motion, no motion, no motion, no motion, up to here, no motion. Beyond this point, there will still be no motion, because basically the net force acting on the object will still be zero. Since there is no motion, we are just defining to be static friction. So the only possibility for the kinetic friction can be, why is the kinetic friction less than but not equal to the maximum static friction? That's the only possible question you can ask. Now that will be, at least if we discuss some of the mechanisms causing the friction, that will probably be more clear. Now, one of the causes of friction is the roughness of the surfaces. So suppose you have these two surfaces, and these two surfaces will not be really flat if you look at it through a microscope. They will have all kinds of hills and valleys, and the surface will more or less look like something like this. This is one surface, if you look it up very close. And if you put on top of it another surface, it will look more or less like this. So this is other surface. So they will just go in each other, like here. So if you try to slide this surface, if you apply a force, this is an external force, on the top surface. Now, of course, these two parts, these two surfaces, it will prevent the sliding motion. So they will not slide through each other. They will not be able to go through each other. So the possibilities are either there will be something breaking. So if you rub two surfaces, you will see that, especially you see it in sandpaper, some of the parts of one surface is left on the other surface. Now either this should break, or the separation between the surfaces should increase slightly so that these two parts will not be going intertwined with each other, these two surfaces. So they should just slide a bit away from each other, and then they will start sliding. Now, once they are, if the two surfaces, they just wait on top of each other, they will just go in each other even further. And if they are just sitting on top, they will just slowly go into one another. So there will be more such regions in the surface. But if there are more such regions in the surface, you need more force to either break all of them or to lift both of the surfaces. You have to exert a larger force. That is one reason why the static friction is larger than the kinetic friction. Because if the surfaces are just moving on top of each other, they will not have enough time to go in one another. It will not be possible. So there will be a very small parts that go into each other, but they will just slide. So that's one of the mechanisms, one of the models, let's say, which explains why the kinetic friction should be smaller than the static friction. Another this is a kind of a mechanical mechanism. You can also have chemical mechanisms, like if you have two surfaces, and this will be especially strong in metals. If you have two surfaces, if they sit on top of each other, they will just form chemical bonds. Now, if you take two metals, for example, take them to vacuum, if you break the two metals, you take two metals, you break them, You separate them in vacuum and you bring them together in vacuum, they will stick as if you didn't even break it. That's what's called cold welding. It's as if they will behave as if they are welded, but there's no heat involved. Kaynak yapılmış gibi olacaklar. When you break it in vacuum and bring them together. Now what happens in atmosphere is when you break them, oxide layers will form. So when you bring them back together, it's the oxide layers that will be touching, not the metals themselves. But still there will be small zones where there will be this cold welding. So if you have, let's say, two surfaces, most of the surface will be covered by the oxide layers, which will prevent the surfaces to touch each other. But nevertheless, there will be these regions which will kind of form some chemical bonds. Now, if you want to move the surfaces, you have to break these chemical bonds, and in order to break these chemical bonds, you have to exert some force. So that's the cause of another source of the friction force. And this model, if the surfaces are moving, this is surface 1, this is surface 2. If the surfaces are moving, there won't be enough time to form more bonds. There will be a less number of bonds forming between the two surfaces than when they are at rest, and hence the friction coefficient will be smaller. Kinetic friction coefficient will be smaller if they are moving. Of course, these are just two models explaining certain aspects of the friction force, but we don't have a complete as of today, we don't have a complete understanding of friction force. We can describe it. We have such simplistic models to describe some of the properties of the friction force, but we don't have a complete understanding of it. So most of the questions about the microscopic description of friction, we don't have an answer for. Now, any questions on friction?
Is it possible that the kinetic friction and the static friction will be an object together?
In what case? I mean, do you have any idea in which circumstance? You see, one of them is related to situations in which the surfaces have relative motion. The other one is related to cases in which the surface doesn't have any relative motion. So these two cases are completely separate. Of course, if you have the motion of an expanded, a large object, some of the parts of the object might be moving, some parts will not be moving. So for example, if you take the in the example of the walking, if you put your hand over here and just keep walking, in my feet there is a static friction between earth and me. In my hand there is the kinetic friction between this blackboard and my hand.
If we have two smooth surfaces but completely smooth, is that still friction force?
Well, in fact, the problem with smooth surfaces is they just click so well. Most of the time, the friction force increases. To very smooth surfaces, you can, depending on the material, of course, the friction force might increase. For example, smooth surfaces, take one stretch film. That is quite smooth.
Why?
As I said, the exact mechanisms of friction we don't really understand. You see, if you have two, in this example, again, let's go back. You see, the only part that is actually very close together is this part. This is the only part that's responsible for most of the friction. These parts are far away from each other. If you smooth this out, that is, if you remove this one, there will be more surface area touching each other. The surface areas close to each other will be more if you smooth them out. So that might be one of the mechanisms.
In the friction force, there are both physical and chemical.
Well, those are at least two mechanisms that we know. Maybe there are others. There seem to be others, actually.
Can we say that the surface tension of liquids is their friction among themselves?
No. Well, of course, due to surface tension, there are insects that can walk on the surfaces, and there is also a friction force involved over there, which is related with the surface tension. Yes. You can do an experiment. I mean, that's an easy experiment to do. Just get some vacuum chamber, put a metal with some robotic arms or with some gloves, break them, stick them together, and they do stick together.
In our description of kinetic frictional force, we didn't take into account speed.
True.
But you stated that as the speed increases, the chance of forming new bonds between surfaces decrease.
I said that when there is motion, the surface, the chance of forming the bonds decreases, but I didn't say that this chance is inversely proportional to the velocity. Well, you see, this is experimentally verified, that this kinetic friction force remains more or less constant. Now, does your model explain that? Well, the chance of forming bonds will decrease. So you are saying that essentially this model is contradicting the experimental observation, so this cannot be the only mechanism. Well, probably not. These are just some models trying to explain certain aspects of the friction force. Probably there's more to it, but we don't know yet. Other questions? Let's do an example. Back to our mass on an inclined plane. And let's assume that initially it is at rest. This is theta. Let's first draw the free body diagram. Now, what are the forces acting on it? There is the weight, the normal force, it's perpendicular to the surface, and in this case there will be the friction force. Is it static or kinetic? Initially it is at rest, so it is static. Okay, so we identified the forces, we drew the free body diagram. Now let's choose some coordinate axis. Let us choose this axis to be the x-axis, and this is the y-axis. Now first the normal force. What are the components of the normal force? The magnitude is in the x direction. We don't know the magnitude, that is one unknown that we have to find. Y, that's true. The friction force is in the minus x direction. The magnitude? The constant times the normal force Is this true? This is not true. We don't know the magnitude. We know the maximum value that the static friction can take. This is the maximum value it can take. But it doesn't have to take that value. Now that is another unknown we have. That is something we have to determine. Let's call it F friction. That's our second unknown. And then we have the weight. What is the weight? In terms of the components. Well, let me just draw it over here. This is the weight. And this angle over here is theta. So it is the mg times cosine theta in the minus y direction and mg times sine theta in the x direction. This is the weight. So we have identified all the forces, and we don't know this n, we don't know this F friction, we have to determine those. Let's first calculate the total force. These are the forces we have. So this tells me that the total force acting on my object is just the vectorial sum of them. So in the x direction, the forces I have are mg sine theta, and then I have the friction force in the x direction, minus x direction. This is the component of the force in the x direction, and then I have the y direction. So the y direction, I have the normal force, this one, and then I have this mg cosine theta in the minus y direction. That is the y component of the weight. Okay, one thing I know, that the acceleration of this object, if it is accelerated, it has to be along the x direction. There can be no y component. So if the y component of F total should be exactly 0. And this tells me that n minus mg cosine theta is equal to 0, or the normal force is mg cosine theta. Okay, one of the unknowns we have already determined. Now, after this point, we have to be, okay, what are we trying to study? Now, we might be told that, okay, the object is not accelerating. So what are the conditions on the parameters of our problem, like the mass, the g, the theta angle, under which my object will not accelerate? So if acceleration is 0, the acceleration itself is 0, it tells me that it's not only the y component, but the x component should also be 0. F should be 0, or for the x component to be 0, we have mg sine theta minus F friction. This should be equal to 0. Or F friction should be equal to mg sine theta. This is the friction force. Now let's see. Let's make an example. Okay, I have this mass sitting on this plane. I can change the angle. I can just lift this plane, so it is at rest, Then comes a value of theta at which it will start sliding. So we can determine that value of theta. You see, this is the friction force, mg sine theta. If we include sine theta when theta is equal to 0, it is 0. There is no friction force. When it is at rest, the inclined plane is horizontal, there won't be any static friction force. It's not necessary to keep it from sliding. As I increase theta, sine theta will increase. But we know that as sine theta is increasing, the friction force will also be increasing. But this is still the static friction force. There is a maximum value that this static friction force can have. We know that if friction, this is the magnitude of the static friction force, that is how we define it, this should be less than or equal to F static max, the maximum static friction coefficient, which we know that it is mu s times the normal force. We had already determined the normal force, so the normal force was mg times cosine theta. So the friction force should be less than mg cosine theta times this mu s. If this is satisfied, the acceleration will be 0. Now the friction force we have determined to be mg sine theta. This should be less than or equal to mu s mg cosine theta. Well, mg's we can just cancel. Tangent theta should be less than or equal to mu s. If this condition is satisfied, then my object will not slide. By the way, this also allows you to determine what the mu s is. Because if you do this experiment, okay, it is at rest, you measure the angle, you increase it the theta very slightly, no sliding, increase it very slightly, it's not sliding, increase it very slightly, still don't measure the angle, increase it, measure the angle, increase, measure the angle, increase, measure the angle, increase, and you keep on increasing until it starts sliding. That gives you the value of theta at which it starts sliding, and once you determine that angle theta, you know what mu s is. So that allows you to determine mu s. Yes?
You said the coefficient can be counted. We haven't found a way to find the coefficient, but isn't this one way?
This is measuring the coefficient. We are not able to calculate it. So we can measure this coefficient. But without being, if we, in one day, if we understand completely what are the mechanisms involved in friction, we will be able to calculate it.
But isn't it generic for all surfaces?
The value?
Yeah, the value.
No, it changes. If I call this one to slide, you see it is some angle. Let's give it okay. So it is at rest. It is such an angle. If I put this one on top on it, let me remove this. It's a smaller angle. So the coefficient of static friction between these two objects and these two objects are different. And there are tables that showing you the values of these parameters. Other questions? So suppose you did this experiment. You just increase the angle until theta became theta max, the angle at which it starts sliding. And then you measure how long it takes to fall down. From that information, you can calculate the kinetic friction. Now let's see how they will be related. So let's assume theta is equal to theta max and tangent theta max is equal to mu s. Now the question is, how long does it take for the mass to slide a distance L. So this is our next question. Now again, this was the question. This is what we have. This is our mass. Now this is theta max. V0 is equal to 0. It's initially 0, but it's 0 just for an instant. At the next instant, it just starts sliding. So since it just becomes sliding, although at the one instant it is the static friction, at the next instant, starting from the next instant, we can use the kinetic friction. Now this expression for the total force still holds. This is still valid. Furthermore, we now know that since the friction is kinetic friction, this F friction is mu k times n, or mu k times mg cosine theta. Because we already know that since my object is not accelerating in the y direction, the y component of the force should be 0. So that allows me to determine the normal force to be mg cosine theta. So the total force is in the x direction. There is the component of the weight minus the friction force, which is mu s mg cosine theta. This is the total force. Or we can also write this as mg cosine theta. Sorry, this is not mu s, mu k. Tangent theta minus mu k, or in the x direction, mg cosine theta. Well, for the value of the theta that we have chosen, tangent theta is nothing but mu s minus mu k. This is the total force in the x direction. This should be equal to mass times the acceleration of the object. So we know the acceleration. G times cosine theta, mu s minus mu k.
It starts moving. So actually, theta max isn't the value for static friction force.
Now, tangent theta max is mu s. It's the maximum value of theta at which it will not move.
Okay, but when we take tangent theta max in this example, we take it for also kinetic friction.
Well, you see, what we are actually doing is theta is equal to theta max. So, if theta is exactly equal to theta max, it will not slide. Theta is theta max plus 10 to the power minus 9 degrees, for example. But that doesn't change any of the calculation.
That's a very good approximation.
Sure. Okay, now does this equation make sense? Let's start with this one. Now, one limit that we can consider is, what if there were no friction to start with? If both mu s and mu k were equal to 0, this equation tells me that the acceleration should be 0. So does that make sense? In the absence of friction, this equation tells me that acceleration is 0? Or does that tell me that acceleration is equal to 0?
I don't think it does.
Why not?
Because we took tangent theta as ms, so if there is no friction, then we can say tangent theta is equal to ms.
Why not?
Because there is no friction and tangent theta is a number different than 0.
What tells you that it should be different than 0?
Unless it's like that.
Okay, so it's, well, you see, if there is no friction, theta is 0. That's the horizontal case. And of course, my object should not be accelerating. Now, I'm looking for the, this result is valid with this definition. So theta should be such that tangent theta is equal to ms. Only under this assumption, this expression is valid, and it makes sense that in the absence of friction, acceleration is 0. Because in the absence of friction, I don't have an inclined plane, I have a horizontal plane. So at first sight, it looks kind of contradictory that in the absence of friction, I don't have 0, I have 0 acceleration. But if you go over the assumption that we have made in order to obtain this relation, like this one, right, there is no contradiction. It makes sense. So we can still take the limit that there is no friction. In that limit, the acceleration will be 0, mainly because of this definition, theta would be 0. This expression would be valid only if theta is 0. And if theta is 0, no acceleration. And so we now know the acceleration in the x direction. We can calculate its displacement in the x direction. We know that the displacement in the x direction would be nothing but v0 in the x direction times t plus 1 over 2 acceleration in the x direction times t squared. This is the displacement in the x direction within a time t, but we know that the initial velocity is 0, or let's say 10 to the power minus 9 meters per second. So we can safely ignore it. And the question is asking us, what is the time for the mass to slide a distance, that is the displacement of the mass should be L. So if the displacement is L, this is given in our question. So L should be equal to 1 over 2 g cosine theta mu s minus mu x times t squared, and we can determine t. Or else, if you know L, you can measure L. If you determine t, you can calculate this difference mu s minus mu x. You know what theta is. G is just a number, 9.8 meters per second squared. So you can determine mu s minus mu x, mu k. And we already know mu s, because mu s is tangent theta. So you can actually measure mu k. You can determine mu k. So this is a means of determining the kinetic and static friction coefficients between various surfaces. You just take two objects made of different materials. You do this experiment. You calculate theta, the angle at which they start to slide. Then you know mu s. And if you measure how long it takes for the object to move a distance L, then from that information you can determine mu k. Now measuring these friction coefficients is not difficult, but the difficult part is how should we interpret them? What are the mechanisms that lead us to a given friction coefficient? Any questions? If tangent theta is smaller than mu s, then it will not start sliding. You see, we determine this theta Because you see this theta is equal to theta max. So this is the value at which my object starts to slide. Now if theta is less than that theta max, then there won't be any sliding. Well, ideally, when it is exactly equal, it will not slide. But in real life, you can never have theta is exactly equal to theta max. There will be always some error bars. So theta will be either larger or smaller. So since you are determining theta max from the condition that it starts sliding, when theta is equal to theta max, it will start sliding. Any more questions?
For you to try to calculate T, you said that theta equals 0 and is non-negative.
No, I said the other way around. If there is no friction force in the system, then this answer, this acceleration is valid only if theta is equal to 0. Because we define the angle theta in relation with the static friction coefficient. So if there is no friction, then this is 0, then theta is 0. I didn't say if theta is equal to 0, there is no static friction.
When the object moves, tan theta is bigger than coefficient static friction, then can we use that as equation?
Well, you see, this. I'm assuming this equation. I'm setting theta is equal to theta max. So tangent theta is equal to mu s. It's not larger. Of course, within error bars. I mean, whenever you are actually setting the angle theta, you will never be exactly theta max. There will be some error bars.
Do you work on the minimum tangent value to slide?
Yes? That is our theta max, or the maximum value of theta so that it will not slide. If theta is larger than this theta max, it will slide. If it is less than, it will not start sliding on its own. And in fact, there is also a range of values of theta such that if theta is within that range, if it's not sliding, it will not start sliding, but if it is sliding, it will keep accelerating. Let's see, there are these two ranges, theta 2. Well, this theta 2 we had called it theta max, such that if V0 is equal to 0, acceleration is 0. If V0 is not equal to 0, let's say, if the object is moving down the incline, it will keep accelerating. So what is this theta 1? So we had already determined theta 2. Well, let's see. We are in this case that it's moving, so it's a case of static friction. Now I will not repeat the drawing of the free body diagram calculating the net force. We already have done that. You see, this is valid. This is still valid. This is the total force acting on my object. I am still in the case of when the friction is kinetic friction, the normal force is still mg cosine theta. So I can just use this result. Now, what will happen at theta is equal to theta 1? So you see, what's happening over here is we have this maximum angle, at which point, if I put my object, it will just stay there. It will not start sliding. But if I give it a push, well, it's not sliding because the component of the weight downhill is equal to the friction force, which is uphill. So they will balance each other, so there will be no acceleration. But if I give it a small push, there will be the friction will be now the kinetic friction, which we have discussed that the kinetic friction is smaller than the maximum value of static friction. So the friction will be reduced. Now, right at theta is equal to theta max, the friction for static friction it's at its maximum value. But if we give it a small initial speed, the friction will be now the kinetic friction, so its magnitude will get less. So it will not be able to balance the component of the weight along the incline. So it will keep accelerating downhill. Now, if I make the angle a bit smaller, what I'm changing is I'm lowering the component of its weight along the incline, so I'm just reducing its magnitude. At the same time, I'm increasing the normal force so that the kinetic friction will increase in magnitude. The component of the weight along the incline will be reduced in magnitude. The friction force will be increased in magnitude. And there will be a point at which they will both balance each other. Now, when they balance each other, if I give it a small push, it will just keep moving at constant speed. There will be zero net force, because the force components of the force along the incline, they will balance each other. The net force will be zero. There won't be any acceleration. But if I lower the incline, reduce the angle theta even further, what happens is the friction force gets even larger. The weight, the component of the weight along the incline gets smaller. So the friction force becomes larger than the component of the weight along the incline. So the net force will be in the direction of the friction force, and hence my object will start decelerating. So you see, in this case, if I give it a small push, it decelerates. In this case, if I give it a small push, it accelerates downhill. Now, right at the value of theta 1, what happens is the total force would be zero. So that it will just move with zero acceleration. For theta larger than theta 1, the total force will be in the plus x direction. For theta 1 smaller than theta 1, the force will be in the minus x direction. You see these two components. As theta gets smaller and smaller, sine theta gets smaller and smaller, cosine theta gets larger and larger. At the value of theta that makes this expression equal to 0, that is the value of theta at which the direction of the total force changes. So mg sine theta 1 minus mu k mg cosine theta 1. This should be equal to 0. This is how we define the theta 1. So mg's, they will cancel, and we see that tangent theta 1 is equal to mu k. At this value of theta 1, if we put the object on our inclined plane and give it an initial speed downhill, it will just move at constant speed. With zero acceleration. Any questions?
Could you explain again when the object group gets zero, that direction upward?
It doesn't go upward. Acceleration.
Yeah, when you push the object, it gets zero.
Now we have this inclined plane. The angle is small. Angle theta is smaller than theta 1. I give it a small push. It just slides a bit and stops. Now what's happening over here, we have this friction force along the inclined plane. We also have this component of the weight parallel to the surface. So the direction of the acceleration will be determined by the one that is larger. If the friction force is larger than the component of the weight along the incline, then the total force will be in the -x direction, which is uphill. So the acceleration will be uphill. But if the component of the weight is along the incline is larger than the friction force, then it will just accelerate downhill. And theta 1 is defined to be the angle between these two regions. You see, if as theta gets smaller and smaller, this component becomes smaller and smaller, this component becomes larger and larger. So there is a value of theta at which these two are equal. That is what we call the theta 1. Now, of course, there you should also pay attention to one more thing. Here we are saying that initial speed is 0 and it is moving downhill. Only in this case it is possible to have 0 acceleration, because the friction force and the component of the weight will be in opposite directions. But if I put my object and give it a push upward, there is no such angle. Because if the object is moving uphill initially, what is the direction of the friction force? It is downhill. It will try to resist the relative motion of the surfaces. The component of the weight along the incline is always downhill. So if the two forces are, if I initially give it a push upward, an initial upward speed, in that case, the component of the weight and the friction force will be in the same direction, and they will not cancel each other. Okay, any questions on this friction force, static or kinetic? It will have 0 acceleration if we initially push it downhill.
The question is, if it is going down the line, it will give acceleration. So it can't be.
No, you see, if V0 is not 0, if it is moving down the incline, no. For this value of theta in this range, it will move, it will keep accelerating. So of course, in the case of the equality sign, the acceleration will be 0. So if you want, I can just erase the equality sign. I mean, you see, in physics, two measurements can never be equal. It can be, they can be consistent with each other within error bars, but we can never be sure that they are equal. So from a physical point of view, whether you put an equality sign there doesn't really make too much sense. Or removing it doesn't really change anything.
So, are you trying to say that, let us say you place an object on an inclined plane and the object accelerates downwards.
Okay.
The object accelerates.
True.
Push, as the object is moving, you push the inclined plane downwards, there will be an imbalance between mg sin theta and mu k mg cos theta, so it will decelerate. If you push it upward above that angle, there will be an imbalance such that mg sin theta will be greater than this, so it will accelerate.
Okay.
So if you push it back to that angle, let's assume you push it up, it accelerates further, and you push it back to the angle, it means that at that point, acceleration will be zero. Is that what they are saying? To be moved by the constant.
Okay.
Is that what they are saying?
True. I mean, as far as I understand, your question is, suppose we have this mass, it is already moving, and we can just change this angle. Now, if we change this angle to theta larger than theta 1, it will just keep accelerating downhill. If we make this angle theta smaller than theta 1, it will just decelerate. So, that's true. Okay, so see you after the break.